Alright, the last method for finding a determinant is called the method of cofactors. This is actually a great method if you have anything large. It works for any size, but it is tedious for anything larger than a 4x4 matrix. So I have our D matrix that we did previously with the values of 10, 8, 1, 192, 9, 11, 7. So what you do is you're going to select one row or column to use to do an expansion. So we're going to do the first row, which is 10, 8, and 1. So what you do is we take each element of this row one at a time. So we're going to start with 10, and we're going to calculate the cofactor for each element. So we do this by ignoring the rest of the elements that are in the same row or column as the element. So we're going to ignore all the elements on the same row and column as this 10. So we're going to ignore this one, and we're going to ignore this one. And what we're left with is kind of like a small submatrix with the values 9, 2, 11, 7. So we're left with that matrix, and it has one fewer rows and one fewer columns in the original matrix. That is referred to as the minor of the element. So as you notice, we're left with 9, 2, 11, 7, which is a 2x2 as opposed to a 3x3. So for the first element of D, which is 10, we ignore the rest. So we ignore 8 and 1, and we also ignore 1 and 9, and we're left with 9, 2, 11, 7. Which is the minor for the first element of S, which is 10. Now, the determinant of this new smaller matrix is then multiplied by either a 1 or a negative 1, depending on the corresponding element's position in the matrix, to produce the cofactor of the selected element. The first element of the first row gets multiplied by 1. And then the second element on the first row gets multiplied by negative 1, with all the elements being assigned alternately a 1 or a negative 1. So it's 1, negative 1, 1, negative 1, 1, negative 1, 1, negative 1, 1, since this is a 3x3 matrix D that we're working with. So it's kind of like in a checkerboard pattern there, and this is something that you should remember for the method of cofactors. So I'm going to show you how this actually applies. So the cofactor for the element D11 is just the determinant of the smaller matrix calculated with the formula shown above for a 2x2 matrix. So it's going to equal to this 1 times the determinant of this one, 9, 2, 11, 7, which is equal to 1 times, we're going to have 9 times 7 minus 2 times 11. Reduce that, we get 63 minus 22, which is 41. Sorry, that's a 7 here. So the cofactor for D12, that's 8 here, is negative 1, we get that from here, times the determinant of, well, we're working with 8, so we're going to eliminate everything in that row and everything in that column, and we're left with the minor, which is 1297. So it's going to be negative 1 times 7 minus 9 times 2 is 18. So we're left with negative 1 times negative 11, which is just 11. Now D sub 1, 3, it's we're going to multiply 1 times, so the element is 1 here. We're going to eliminate everything in that row and then everything in that column, and the minor for that element is 19911. 1, 9, 9, 11. So it's going to be 11, or 1 times 11, so 11 minus 9 times 9, which is going to give us a negative 70. So the determinant of the original matrix, D, is then calculated by multiplying every element of the selected row, so it's going to be 10, 8, and 1, by its cofactor and summing across the elements of the selected row. So the determinant of D, 10, 8, 1, 1, 9, 2, 9, 11, 7, is going to be equal this first element, 10, times its cofactor, 41, plus this next element, 8, times the cofactor, which we found to be 11, plus its last element in the selected row, which is 1, times its cofactor, negative 70, which is going to equal 410 plus 88 minus 70, which is going to give us 428, which is the same value we found using the other methods and also using Excel, which we did in video 3.24 when we first introduced determinants. So that's the last method, the method of cofactors. Once again, it works for any size, not just a 3 by 3, but it does get tedious for anything larger than a 4 by 4 matrix. There you go.